Hey everyone, today we're going to be talking about a really important concept in this unit. This is probably the biggest lesson in the unit in the sense of how much you're going to be using it. We're going to be talking about this thing called the law of conservation of energy. I'm going to write that out. The law of conservation of energy. And so think about a little bit what that means. Law of conservation of energy. It basically has to do with how energy is conserved or kept or stored in a system. And this is the subject for today. Now, we're going to need to start with a little bit of background info really quickly. And these are types of systems. We've dealt with kind of the concept of a system, which is really just all the things that we're dealing with in a specific question, like all the objects. But there are three types of systems, and we kind of need to know this to understand the law of conservation of energy because it only applies to one type. So the three types of systems. The first type of system is an open system. The second type of system is a closed system. And the third type of system is an isolated system. And open, closed, and isolated systems differ in what is allowed to enter and exit the system. Basically, open, if you have matter and you have energy in a system, because that's usually what you have some matter, some object, some stuff, and they have energy. An open system, both matter and energy can be exchanged with outside the system. I'll give you an example. If you have a pot making pasta on the stove and the pot is open, that is an open system. The heat, the steam is leaving and going in, the energy from the stove is entering, so there's transfer of energy back and forth, and obviously you're putting water in, you're putting salt in, you're putting pasta in, taking it out when it's done, there's also transfer of matter. Now, closed systems, when you have matter and energy in a closed system, they do allow matter to enter or leave, but, they don't allow matter to enter or leave, but they do allow energy. So no matter, but energy can. This would be if you took that pasta pot and then you put a lid on it. Well, now you can't exchange pasta or anything, put salt in, take stuff out, but the energy from the stove is still entering the pot and it's still leaving the pot, and that thermal energy is being exchanged. And finally, because there's only one combination left, you can probably imagine what an isolated system is. An isolated system does not allow matter or energy to go in or out. That's if you took this pot of pasta and put it in an isolated, kind of thermically sealed box where you cannot take anything in and out. There's no thermal energy back and forth. It's isolated. Getting a practically isolated system is quite easy. Getting a perfectly isolated system, much harder. But this is important because the law of conservation of energy applies only to isolated systems. If the system is open or if it's closed, you cannot rely on the law of conservation of energy. This isn't as big of a problem as we think, though, because a lot of the questions we're going to do, we can assume the system is isolated, even if it maybe wouldn't always be in real life, and I'll explain why that is in a little bit. So, on to the actual law. The law. The law of conservation of energy is stated like usually in a textbook like this, and then I'll explain what it means in better words. It says that energy cannot be created or destroyed in an isolated system. It can only be transformed from one form to another. So there's two parts to this law, and so the first part of that law is energy cannot be created or destroyed in an isolated system. Everything I say from now on is going to assume in an isolated system, so I'm just going to stop saying that with every sentence. But energy cannot be created or destroyed. This is really unintuitive to most people who think, well, of course energy can be created and destroyed, that only makes sense. But energy cannot be created or destroyed. All energy does is it changes type and it changes where it is. I'm going to give you an example. If you had a good night's sleep, you wake up and you're super ready for the day and you're going to run a 5-kilometer run that day. You've been storing up energy, your body has a lot of energy, and you're going to use that energy, that kinetic energy is how you're going to use it when you're running. Now, as you run, you're going to get more and more tired and tired and tired. You're using the kinetic energy. You would think that energy is just disappearing. But that energy isn't going nowhere. It's simply changing type. that kinetic energy is being repurposed into thermal energy, which is why you're sweating, which is why you're probably feeling warmer. It's being repurposed into all sorts of types of energy, chemical energy, etc., and it's just leaving the form it was. But if you were, theoretically, if you were an isolated system, which again, in reality you're not, and you were to measure the energy before and after, that net energy before and after would be the same. Energy does not get created and it does not get destroyed in an isolated system. It is only transformed from like kinetic to potential or from chemical to thermal, but never created or destroyed. Now this is super useful, and it might not become immediately apparent why it's useful, but really is, and a lot of the reason for that is in questions. You can assume that you're in an isolated system usually, unless it tells you that you're not, and therefore you can assume that the total amount of energy in that system is not going to change. So if you know one amount of the energy and you know the total, you can find the other amount of energy, and if those amounts of energy change, you still know the total will remain the same because that total cannot change because of the law of conservation of energy. This will become apparent when we do test problems, when we do more questions later on, but for now, this is why the law of conservation of energy is so useful. Now, one kind of, side note here. The law of conservation of energy, like that, would be including all types of energy. That means thermal, chemical, elastic, kinetic, potential, gravitational, all these types of energy in one. And so for the same reason that we usually don't use net energy, remember, it would just be so overwhelming to deal with all these types of energy, we also don't usually use the full law of conservation of energy. Because, again, that'd be very impractical for most questions. The majority of questions we're dealing with in this section of the unit, you'll remember, only involve two types of energy. They involve kinetic energy, and they involve gravitational potential energy. And these two types of energy, gravitational potential, these two types of energy are really the main ones. And if you remember, when you combine these two together, you get something called mechanical energy. And because we're usually dealing with mechanical energy, there's a second law, and it's called the law of conservation of mechanical energy. So not just law of conservation of energy, law of conservation of mechanical energy. Because some systems in the world will just deal primarily with mechanical energy. And that means that not only will they obey the law of conservation of energy overall, but they will also obey the specific part of it dealing with mechanical energy. That means that the kinetic and gravitational potential energies added together will stay the same the whole time. Now, this is not true of every system. For instance, the system of you running is not a system that obeys the conservation of mechanical energy because your kinetic energy is getting transferred into something thermal, which is not one of the parts of mechanical energy. But a lot of systems, and most of the systems we'll be doing in terms of questions in this unit, involve kind of inert objects like, balls or roller coasters, or, even like people walking down the stairs, where we just forget about most of the other types of energy and just deal with kinetic and gravitational potential. And so you can assume this thing about mechanical energy, namely that the mechanical energy at time 1, at initial time, is going to be equal to the mechanical energy at time 2. This is usually the assumption we can make, and it's extremely helpful. I'm going to do this with another example, and it's a familiar one because we did it last time, and it's a rock that's on top of a hill. And if you remember, the rock was being blocked by some barriers so that it could not go down the hill. And I was explaining some stuff here, namely that this rock, at this point, has a large amount of gravitational potential energy. And then as it rolls down that hill, you get kinetic energy, and it goes down, and you get kinetic energy. But what I didn't explain, and what I'm going to explain now, is that the amount of energy in this rock never changes. Not at all. But what does change is the type of energy. It transfers from gravitational potential energy to kinetic energy over the course of the trip. So, to just pick literally a random amount, let's say this had 100 joules of energy at the beginning. So, Eg equaled 100 joules. I can guarantee for you that if you picked any point on this path, let's say like right here, that there would be a certain amount of gravitational potential energy and there'd be a certain amount of kinetic energy. And I don't know how much of each, you could calculate it if you had enough information, but they will equal 100 joules when you add them together. And that's no matter where you do this, because the 100 joule total will not change. Here, when 100 joules is gravitational, there is no kinetic energy. And that's because the thing hasn't started moving, it just has potential. When you remove the barrier and it starts moving, you're going to slowly start transferring gravitational energy to kinetic energy. You know, you might get 1 joule of kinetic energy and 99 of gravitational around here, and then, 98, 97, transferring it over to the kinetic. And I don't know, by the time you're here, you might be at 50-50. And it's going to keep going all the way until you're at the bottom, and you've transferred all the energy to kinetic, and you have none left in gravitational potential, and then the ball will stop, and you will have ended your course. This is the principle of this conservation of, in this case, mechanical energy, and this is what's going to allow us to solve problems, because it's useful to know that no matter where we are on this path, the sum of those two values is always 100 joules, or whatever value. Alright, there's one last topic that we need to cover in this video, which is kind of indirectly related. And this topic is the concept of conservative forces. Conservative forces. And there are conservative forces, and there are non-conservative forces, because not every force is conservative. And so what is the difference between these two things? Well, I'm going to attempt to explain. A conservative force is a force where the amount of work that's being done is independent of the path. Now, when I say the path, I just mean that it doesn't really matter what direction, or kind of if it's zigzagging or like going up and down, doesn't matter. As long as you have the same kind of force and you're dealing with the same mass, those quantities are the same. If you have a force where the path doesn't matter to the amount of work, then you have a conservative force. If the path does matter to the amount of work, then you have a non-conservative force. So conservative forces are things like gravity, electric force, magnetic force, even nuclear force, or elastic force, although elastics needs a bit of like an asterisk. There's something a little more complicated about that we don't need to worry about right now. You know that gravity is a conservative force because gravity is just always given by the equation, if you remember, Eg equals mgh. So it doesn't very much matter the path, because you can see that the path does not factor into this equation at all. It just depends on mass, force of acceleration due to gravity, and the height, the delta h. That's it. And so gravity is a conservative force. A lot of these are also conservative forces. As for non-conservative forces, things like friction, things like air resistance, which is technically a type of friction, things like thrust, as in like from a rocket, and things like tension are non-conservative forces. Friction is very, very complicated. We went into the simple basics of it in the last unit, but it is complicated, and a lot of it does depend on path. You can generate more friction by zigzagging along the surface than you can by going straight, and etc. Now, the use of knowing whether your forces that you're dealing with are conservative or non-conservative is they tell you how to solve problems with them. And this is very simple. Conservative forces are always solved with this specific equation, which is ET1 equals ET2. And we've met this equation. It's literally the law of conservation of energy, that the initial energy will equal the final energy. T for total. You might be using the mechanical version where that T becomes an M. But that is how we solve for things that are conservative forces. If you're dealing with gravitational potential, like we were in the question on the hill, it's a conservative force, so we use these conservative force equation. If you're dealing with non-conservative forces, you cannot rely on that necessarily, so you instead work with a different equation, which we've also seen, which is total work equals change in energy. And this is from previous videos, you've seen this, and this also makes sense, but it's the way you solve non-conservative forces. So remember, conservative forces, ET1 equals ET2, non-conservative forces, work equals delta E. This is about it for this video. It wasn't too bad overall, but this is a very important concept, so make sure that you understand it. Remember what we've gone through, the law of conservation of energy and its counterpart, the law of conservation of mechanical energy that just deals with kinetic and gravitational. We looked at open, closed, and isolated systems. Remember that these laws apply only to isolated systems, but in a lot of questions you can assume that the system is isolated even if it might not be in real life. And finally, we looked at conservative forces and non-conservative forces and which equations to use to solve problems with these. That's all for this video. Thank you very much for watching, and I'll see you guys next time.